Good morning, good evening, everyone. Welcome to another episode of Xah Talk Show. We are going to do Advent of Code 2025, Day 4, Part 2, Take 2. So yesterday we began to do it, then we got distracted into talking about a demonstration of what is Wolfram Language, Mathematica. So you can watch yesterday a great introduction to Wolfram Language. Hello, that beast. So this is yesterday's talk show, Wolfram Language. Let me check audio, check video, check. Okay. So Wolfram Language, symbolic algebra, graphic system, Julia set, animations, and generating sound, synthesize sound and play it, and 3D graphics, interactive, and geography, and graph theory. So Wolfram Language can do lots of things. So that was yesterday. And so today we're gonna continue this Advent of Code 2025, Day 4, Part 2. I'm going to try just to code it. So in previous weeks, I talk a lot. I talk as I code and I give analysis or opinions about different things. Today, let's try something different. So I'll just try to code it without much talking, but I'm going to explain what is the problem first, okay? So if you are watching this offline, play at 1.5 speed or 2 times as fast. If you are here, say hi, okay? So the problem is that Advent of Code 2025, Day 4, Part 2 is that you are given, can you see it? Yes. So you are given this text file, a grid, each @ so you have many @ and some dots, okay? Now for each position of the @ you want to find the neighbors. So you have neighbors, including upper right, including diagonal neighbors. If it has less than 4 neighbors that are @ so you want to count @ around its neighbor. So it has less than 4, then you consider that @ special. So you go through each @ look at its neighbors. If it has less than 4 @ around it, then you consider that particular @ special. Okay, so you go through that. Then the problem, part 1, is that you want to determine how many special @ are there. So problem part 1, the solution is 13. Okay, I mean the toy solution is 13. This is 13 right here. Okay, my personal answer is 1527. Okay, so part 1, find how many @ that has @ neighbors that are less than 4 of them. Okay, now the second problem, part 2, which I'm going to do now, is that for each @ you find the special ones that has less than 4 @ around it. Okay, once you found it, you remove that @ okay, then you repeat this process. You do it again. You found the @ that has less than 4 @ around it. You remove that. Then you repeat until there are no @ that can be removed. In other words, you end up with this picture where each @ has at least 4 @ around it. Okay, so the problem asks, in the whole process, how many total @ you removed. Okay, so that is a problem, and I'm going to code it without much talking. Our MacBook still top tier for programming and software, SWE. I don't know what is SWE, software something, but MacBooks. So if you use a computer, mostly for the purpose of coding, like I do. But actually, I use also lots of things. I use it for well, watching videos, but mostly coding. Okay, so if you use computer for mostly coding, your great choices are Mac. Mac is a great choice in general, and also Linux. Okay, but if you also play video games or if you explore virtual reality, uh, or you or explore lots of other programs, then Windows is is common choice. Okay, so let me start to code. Okay, without much talking. Let's see. Let's see if I can finish it fast. Maybe in 20 minutes. Today's drink is tea, black tea, hot. So I'm just gonna go relaxed. Okay, so play at 1.5 speed or 2. Okay, let's start to code. Showing browser. So that's today's talk show notepad notes. Okay, so section go to let's start to code. Wolfram language I introduced so much I don't need to. Okay, let's just start to code. So let's go to. I'm still gonna talk a little bit, but I'm mostly just gonna focus on coding. Okay, so we need to copy the previous code. Clear neighbors. Okay, copy that. Is this the right code? Yes. Okay, paste it there, and also we need this solution. Okay, I mean the previous input. BSD based, not Linux. Hardcore tech geek BSD. Congratulations. Okay. Code. So I need to code. So turn it into a matrix of 0 and 1s, and we got this get neighbors and we got these dimensions. Do we need dimensions? No. Okay, so dimensions. Let's see. Okay, delete that. Okay, that's what we need. Matrix 1, 2, index num positions, and then neighbors. Okay, neighbors we delete because we okay, that's our code. So input, so here's the input, turn it into a matrix of 0 and 1s, and here's the get neighbors, and then here is the main. All indexes where cell is a paper row. Okay, index of paper row. So you get the position. So each round, so you get the position, then you need to count, you need to tally. So you get a bunch of positions, then you apply total, right? So you apply this function. You apply this function, so you need to replace that variable, get neighbors. Okay, so so each time you do this, you need to remove those cells, remove it, and you need to repeat. So each time, I need to write it down. Each time input is a matrix. Go through the matrix, remove some cells, repeat until no cell can be removed. Count number of cells removed. Get total number of cells removed. Okay, that is the essence of the algorithm. So you write a function that takes a matrix, then it returns the matrix. Okay, let's plan. Write a function ff. It takes a matrix and return a matrix. Okay, but no, but every time it does, we're gonna do this in pure functional way. So every time this does, so it takes a matrix. It takes so the function will have a signature like this. Current count of removed cells. Okay. So the function will take an input matrix, current count of removed cells beginning with 0. It will return a new matrix, and it will return a list, and the list is going to be new matrix and new total removed cells count. Okay. Then, so the function takes a matrix, current count of removed cells, and return a new list. New matrix, total removed cells. Okay. And let's make this into one single input so that it can recurse by itself. Then use nest fixed point. Then the solution is fixed point ff. That's right. Fixed point will recurse a given function until result no longer changes. That's right. Look up the documentation, fixed point f expression. Okay, you need the initial expression. Yeah, so fixed point, then input matrix 0. Okay, that is the plan. Argos step. Okay, now we're just gonna write this function. So the function will have this form. Okay, input matrix current count of removed cells. Okay, then it will do whatever we're gonna do. So block is a local variable. Okay, basically group the whole body of the function like Lisp's PROGN. Okay, then input matrix. So so we kind of need this part. Okay, so let's move that somewhere here. Okay, so this function we define like that, and so you each step you need to total. So this gets a total. Okay, so this code just gets a total of special cells, that is also known as removed cells, going to be removed. Meanwhile, you need to return the matrix, so you can see you can say cells to be removed. Okay, that's one variable. And result matrix, that's another variable. And in fact, you reverse the order. Okay, two local variables. Okay, and what you do, so becomes simple and simple. So this part is the cells to be removed. Okay, then it just return that. Okay, now this part, cells to be removed, is already done, computed there. Now the new return matrix, how do you do that? Well, given a matrix, certain positions in it needs to be removed. You need to know those positions. Okay, so you need a variable, positions list. Okay, to remove position list. Okay, we make our variable long, so it's like readable, so people can understand it. Okay, so we make our variable very long. This is in contrast to C and C++ idiots style. Wolfram language typically have long descriptive names, all the built-in function, like that is the tradition basically from Lisp. That's a Lisp tradition. Names are usually very long, descriptive. Okay, so this is critical. To remove positions list. How do you get that? Once you know that list, you can easily delete it. Delete those positions by let's how do you do that? So result matrix, let's color it. Okay, result matrix equals to something. Okay, yeah, result matrix equals to delete well, it's gonna be map delete to this to remove positions. Then that will return a new matrix assigned to the result there. Okay, then you just return that. Fantastic and beautiful. So now the job is to define this to remove position. Okay, but first of all, let's look up the documentation for delete. Right. Okay. Now let's do a test case just to be sure we got this right. Okay, so delete in this matrix, and you want to delete position 2 2. It'll return 1 2 3, then 4 5, then 7 8 9. Run it. Annoying when you start Wolfram language. You see? Perfect. Perfect. Three, Shift Enter to start it. Magnify 150, enlarge. Okay. Copy that. Paste it. Shift Enter. Fantastic and beautiful. That's how it works. Now, the question is, how do you get this to be removed position list? Okay. Well, that part, the code is similar here. So, so you need to actually, hold on a second. This list will equals to something like that. Okay. Now, forget about total. Now, let's see. Let's make it more legible. So, okay, I know what to do. So you let's see. Position. Let's look up the documentation. Position return an element's position via a pattern. Position, expression, and pattern. Given an expression, if a pattern matches any part of the expression, it will return a list of all those positions of that matched expression. Okay, so this is effectively given a list, could be a tree nested list. You want to get all the positions such that the element matches this pattern. Okay, that is what this is doing. Okay, so the matrix is our input. So input matrix. Okay, now what are the patterns? How do you match a pattern? The pattern needs to be such that, you know, it has less than 4 neighbors. Well, this function will tell you this get neighbors and less than 4. So this okay, so this needs some work. Okay, now where is this index of paper rows? Oh, that's not defined. Is it defined? Oh, it is. Okay, all indexes where the cell is a paper row. Oh, so every time you need to do this again. So this needs to be moved inside the function. Okay, so okay, so now now it's getting a bit complex. We need to clean up a little bit. All indexes where the cell is a paper row. Okay, So first of all, copy that. And move this here. Okay, so we got now 4 local variables. This should be count, okay? Okay, it's getting closer and closer. Save it, make a backup, close it, reopen. So we got a thread, we removed the highlight, okay? So again, this function, local variables, index of paper rows. Okay, actually, let's rename it. Fuck. Rename hell. Let's stop that. Okay, position of paper rows. Now this is inconsistent naming. Bad. Assign position list. Better name. Now this to remove position list. Okay. Now it's more consistent name and even shorter. Assign positions list. List of positions. To remove positions list. Result matrix. To be removed count. Now it's better. Now highlight them. Okay, let's begin our journey of coding. So assign position list, that gives you all lists, all indexes, all positions where the cell is a paper row. Fuck the paper row. Assign. This is very inefficient, but we don't care because advanced code, they don't appreciate efficient codes. They just care about an answer. This is inefficient, but don't care, okay? Assign position list, okay, you got that. To be removed, to remove position list, this we don't know yet, but first of all, we need the so this is to be removed count. We can move that there, okay. Now, okay, so that, and to remove position list. So how do you do this? So you map this function, wait, to this, basically map index, okay. So actually, now let's experiment a little bit, okay. I needed to have like some test. So the matrix is that put it back, create a new Wolfram code, and you need to do some testing, okay. What? Yeah. Okay, let me concentrate. Map a function get neighbors, map a function get neighbors, so it returns, so map assign position list, so you map position, right? So you map that to a list of positions, and each become, okay, so hold on a second. So let's modify this. So let me show you what we're gonna do. You map a function to assign position list, and what function you're gonna map? Here is the trick, okay? Here is the function you're gonna map, but hold on a second, let me clear it for, okay? You're going to map a function such that, okay, here, focus on here, okay? Here, we're gonna write this function, one shot. We don't need these two lines. You're gonna map a function to this list of positions. Okay, wait, what? Hey, how did that get there? Oh, okay, hold on a second, okay? Remove that, okay? You're gonna map a function that is a function, okay? Map a function, the argument is x. Now what does the function do? It's a if statement, if expression, okay? If get neighbors returns a list and total them. If it's less than 4, you don't return 1, you return the position, which is x. Okay. Otherwise, what do you return? Nothing. This is a tricky part. Okay. Nothing in Wolfram language is like nil or null. Basically, when you have nothing in a list, this nothing automatically disappears. Okay. It's like nil, null, or undefined. You know, in programming language, you have this 1 billion mistake. Nothing represents an element of a list that will automatically be removed. Okay, this is new in when is it? 2015, 10 years ago. When I was coding heavily in Wolfram language, I don't have this, but now you can have this. Okay, so if let's make sure this is correct. Okay, you map a function, that function, to or the positions of the at list. Okay, if the total you sum it up of all the neighbors is less than 4, you return x, which is a position. You return that position, otherwise nothing. Okay, another way to do it. Okay, now we remove this part so we doesn't get confusing. We are coding this part to remove position list. We want a list of positions we want to remove. Okay, in fact, we don't need to do this map. In fact, we can do, let me hold on a second, let me think. This will work, but there are better way. But hold on a second. Let's not get distracted like, oh, but there's a new way, let's try that. No, but then there's another way, let's try that instead. Then you never finish. So let's just stick with okay, so to remove position list, that should work. But actually there is a better way. Okay, you just say, don't map. Okay, don't map this. Okay, you want to filter this @sign position list. You see, it's a list of positions. You just want to reduce them. For each position that needs to be removed, you remove that position. Okay, so you reduce this @sign position list. In that case, you can use cases or select. Okay, so select is like filter. Okay, data and criteria. Okay, let's do that. Select, let's make it simpler. Okay, select, filter. Okay, select from this list what is the criteria. Well, the criteria is this function basically. Okay, this function, if total something something is greater or equals to 4, then true, else false. Okay, is this simpler? Yes. You see, select 2 arguments, data and criteria. The criteria is a function. Okay, so that, so you see, hold on a second. So you see, we have 2 implementations of this generate the list of positions to remove. Yeah, I'm pretty sure it work. Okay, so let's get on. Let's finish the problem. Okay, this function, so far so good. You guys watching, it is superb functional programming. Superb. There's no variable mutation. There's no for loop. There's no plus plus like the C++. Fuck. There's no objects. There's no iterator, there's no accessor, there's no constructor, all those facts. All these are pure function. Position, a necessary concept when you have a list or indexes. Position, matrix, all these concepts are fundamental and necessary because they came from mathematics. None of the accessor, iterator, generator, the object-oriented stuff. Okay, so assign position list. Then to remove position list. Then actually to be removed count. You don't need you can just to remove you just count the length of the that. Then so you see we improved so much. Let me do alternative code here. You see, now the to be removed count is just that. You don't need this anymore. Is that right? We need to think about it to be sure, okay? So one more last check. Assign position list. Then select with this criteria. So this should be less than 4, not greater than equals to 4. Neighbors less than 4. That is true. Yeah, we got to make sure that is right. Yeah. To be removed position list. Then the count is just length of that. Okay. Then the result matrix is you map delete to this list. Actually, you don't map. You just let me show you. Okay. You don't map. Okay. You simply delete. Yeah, this is incorrect. Delete the input matrix by this to be removed list. Okay, all those positions, delete them. Then return result matrix and remove count. Now let's rename again. This is not to be removed. Ban the word to be. Very complicated. Rename it. Just remove count. Very critical. Naming of things. Okay. I think we're done. So let's compact the code. So the code is just that. Okay. It's probably unreadable to you. So let me just remove these comments. Let's put the comments to there. So just in case we need them. Okay. So now the function is simpler. Can you see it? This function, input matrix, current count of removed cells. Oh, you need to add them. So the remove count needs to add plus current count of removed cells plus new remove count. That's right, because they need to accumulate. Okay, so this is the return value. When you have a bunch of expressions, it returns the last expression, return value. Fantastic. Now the final solution, just call this, okay? Let's see, final solution, fixed point, FF, input matrix 0. Then it will return this list. The first part is the matrix. The second part is just a number. And if we run this one shot, this is like one shot coding. There's no trial and error. I wrote this in my head. We run this. Will it give us the solution? Okay, let's check one last time. Compact the code. We don't need this comment redundant because now the naming is clarity at sign position list. So let's check one more time. This function, and since now each variable is used once, we can actually replace the block local variable dynamic scope by a width, which is constant, local constant. We can do that. You just need to make sure that they are not used, they are not mutated, they are not. But however, this variable uses the value of previous variable, so you actually need nested width local constant. That's not good. Let's just leave it like this, okay? Assign position list, remove position list, result matrix, x remove count, okay? Input matrix. Now, where is input matrix used? Let's see. Input matrix. Where is the input matrix used? That's not good. Oh, yeah, so you forgot. It should be here, not X matrix. Oh, you gotta be careful, okay? Not X matrix, my friend. That's input matrix, okay? And you got X matrix here. Yeah, that also needs to be input matrix, I think. And what is this delete X input? Oh God, you be careful. You don't want to fuck up. Okay. So you see input matrix. Okay, save it, close it, back up, close it, reopen, fresh. Now input matrix is a thing. This rename that variable. Let's just say count of remove cell, okay? That's too long. Remove count, okay? Input matrix, remove count. Okay, colorful. And in fact, you don't need remove count because remove count is this expression and you just replace it there. You don't need it, that variable. Result matrix delete to remove position list, okay? So far, so good. So far, so very good, I think. Now, let's copy that. Is mature enough to put into Wolfram language, Wolfram notebook, so we can see how it formats. Actually, we can run it. Is there a syntax error? No. You see, the Wolfram language formatted on the fly well with all the indentations created on the fly as part of the rendering, not hard-coded space or return or tab, like the Python, C, C++, Java idiots, industrial coders. It's like a long form essay. One thing, let me digress again. Okay. One thing about Wolfram language is everything you can make it into one line. That's still valid expression. Okay. I'm so used to this. Like I can make my whole program one line. Well, except when you have text string. But other than string, which is kind of hard-coded syntax within a programming language. But otherwise, like Wolfram language, you can make everything one line. Okay, that's still valid. Which is true too for Lisp, except the stupid Lisp comment. Like I can show you stuff like keys. Go to my Emac Lisp code, except Lisp can do that too, except for example, this go to previous buffer. That's what this key do, go to previous buffer or go to next buffer, back, next, back, next, back. Okay, that's what this function does. Okay, now I can make it one line, still works. Okay, this also has this property, except this idiocy, this comment. When you have this comment, you make it one line, is fucked up. It no longer valid, this code, because the common syntax has a stop the show flaw. That is, it relies on a new line, a line break, a hard-coded formatting character to work. It serves as the delimiter for the end of comment. See, the common syntax, Lisp fatal idiocy. Because of this, the Lisp syntax perfect nesting can no longer be freeform, But if you don't have this comment, this still works. Okay. But then if you have this comment, then you make it one line, it stops working. So very annoying. So a remedy I've been thinking is that just make all your comment a string. But that's inefficient, because string, it will evaluate. But when you have like well, you can't actually put a string here. Yeah, so you got some issues. Okay. So that's a Lisp problem that basically you cannot fix. Like in Emac Lisp, you cannot like create a new function so to fix it. No, it's part of the like fundamental syntax, this common syntax, a fatal flaw of Lisp. Okay, anyway, make sure I didn't change anything in Xah keys. Close it. Okay, close it. That's a digression. It's previous buffer. Okay, let's go back here. Yeah. So are we ready? Just copy the whole thing and run it. Okay, let's remove this. I think so. Okay, let's see. Will I fail? Maybe. If you bet me $100, then I'm gonna check one more time. Okay, but since nobody is betting, does anyone want to bet $100? Like I run this one shot, it's gonna work. Okay, so begin by the input a string block of text. We turn this by this fantastic expression. We turn it into a matrix of zeros and ones. Okay, then we define this getNeighbors function we defined in previous days. This can be much improved anyway. Then we describe today part 2's algorithm. Each loop you need to remove certain member of the matrix. Okay. Then we defined, so the essence lies a new function, this ff. In functional programming, it would be better if you give it a proper name, like remove, let's name it remove cells. But you see, in mathematics, in mathematics, if you read, for example, mathematical journals, topology, graph theory, usually they have gamma, alpha something, like summation or integral. You don't see a name like this is a cell, like current cell or to remove list. You don't see that. Every symbol is just usually a single character. Alpha, gamma, beta, zeta function. So I'm very used to a function, just ff. Okay. So anyway, this function ff takes a list of two things and return a list of two things. Then at the end, you just fix. Let's just run it. Okay. I started to talk too much now. Let's yeah, this is one single cell. Let's run it. Let's see. Please, no error, please. Okay, it is wrong because there is no such thing as input matrix. God. Okay, so let's write X matrix. You got X matrix, but okay, so yeah, this is wrong. This is X. It should be X matrix. Okay. Okay, let's just do that. Let's just copy this line, actually just copy it here and back to Wolfram language and call this function. Shift enter, please. Why is X matrix not defined or something? X matrix. Oh wait, X matrix capitalization. Fuck. Where did I just got so fucked with this this capitalization? Why did it yeah, it shouldn't be capitalized. Okay, let's fix this. No capitalization, please. Now, run it, please. Fuck. Part specification. I got this wrong. Now, where does it come from? Oh God. Longer than depth. Okay. Okay. So what is all this color? Okay. Put it back. Make a backup syntax color showing browser. Okay, one shot. Incorrect. So now let's do it again. Okay, so it says something about part specification, fixed point, part specification. Longer than depth. Okay. Okay, yeah, well, you need to debug. We did this like without trial and error at all, but it's not, Wolfram language is not pleased with my one shot. Something is wrong. So where is this input matrix? Yeah. Like this will work, right? So okay, we need to debug. Okay, this returns @ position list. Yes. Okay, Then this returns to be removed list. Wait, didn't we change them? To remove list, position list. Okay, let's try it. Do it. Okay, that's the problem. What the fuck is your problem? Select criteria. Select even Q. Okay, we select it and pick out all elements EI of list for which criteria EI is true. Okay, so select is our function. The first argument is assign position list. Oh wait, obviously no. You use the wrong list. This should be the input list. Wait. Oh yeah. So I know what's going on. So you use the wrong list. Okay. So select assign position list by this function. So let's fix it. You see, by this function, and this function needs to be what? So do we have a like, okay, precedence? We got it correct. Get neighbors input matrix. Oh wait, in this is X matrix. Okay, run it. Yeah, that works. That works. Confusing name. So let's check. Let's rename them. Okay, let's not rename them. Well, this input matrix. So let's just say so that it is more. So it worked, right? Yeah, once you get the matrix assign position list. For this position list, you want to remove some of them. Wait, to remove list, right? So the one you want to remove is get neighbors of the X matrix, the input matrix. And X is the position because it applies to each element in the position list. So X is the position. So get neighbors of this matrix at that position, and if the total is less than 4, then true. Means oh, it means keep that. Okay, so you want this, you got this wrong. So it must be greater than equals to 4. Right, that means to keep or reverse the true and false here. Okay, so if it's less than 4, to remove list. Wait, let's see. You got list of positions to remove, so it's less than 4. True. Wait, okay, so to remove. So what is 1 3? 1 3. So this at sign No, that shouldn't be removed. 1 3 1 4 1 6 1 3 1 4. Wait, did we get the logic wrong? So if less than 4, so 1 3 is a add sign, 1 4 is a add sign, and 1 6 is a add sign. Check. And to remove list, so it says 1 3 should be removed because it has 1 2 3 neighbors. Check. Then 1 4 should be removed because it has 1 2 3 neighbors. Check. Then it says 1 6 should be removed because it has 1 2 3 neighbors. Check. Then it says 1 7 needs to be removed. What? 1 7 because it has 3 neighbors. Then also 1 8 and 1 9. They all needs to be removed. And 2 1. Then second column, first one, yes, needs to be removed, but not 2 2 because 2 2's got 1 2 3 4 5 neighbors. You see, not 2 2 and not 2 3, correct? And not 2 5 neither. Wait. 1 2 3 4 5. 2 5 has no, not 2 5 because it has neighbors 1 2 3 4. Yeah. So the next one you want to remove is 3 7. So let's check. Stay. 3 1 2 3 4 5 6 7. So this one needs to remove. That is correct. So our to remove position list seems to be correct. Okay. I'll put this back so it don't wait, what? Okay, so what else is wrong? So to remove position list is so far so good. Yes. To remove position list so far so good. Yes. And then you have remove count. Could it be wrong? I don't think so. Shift enter 13. Yeah, that's right. That's right. Then you return this. Then what? Wait. Then result matrix. Right. Then you need to compute the result matrix. Okay. Oh, you don't delete, my friend. You don't delete them. You replace it with a. You don't simply delete them because if you just delete them in this matrix, the matrix shape collapse. You know, some row will have less columns, so it's no longer a matrix. So we found the bug. So you don't delete them. This is incorrect. You want to replace it by 0 instead. Okay. So what is a way to replace? Well, I forgot. So let's showcase my Wolfram Language tutorial. Search for it, Xah Wolfram Language tutorial. You'll find it. So you go to number spooling list. Then you go down length. Vector is a list introduction to vector array, matrix, tree. They are all represented by this single syntax list. Okay. Then you go to list operations. You want to change parts, add elements, delete elements, change elements. Okay, that. Replace part by position. Okay, that's what you want to do. So is this interesting? So I need to have some more tea. We are almost done. Almost done. We've been going on for 90 minutes. Jesus. Coding takes a long time. So hold on a second. You want to now we want to replace parts. Right. So if you give a single number, then that's the index. So, but if you give a list, then that's the position. Right. So you gotta have you get these the positions then. Okay. So instead of that, now let's code it here so that we can actually wait, result matrix is the part you want to fix, okay? Not that. Okay, so let's code it here. Copy it, not delete. So instead you want to replace part. That's right. Replace part of the matrix, X matrix, and okay, well, so what you do is you wouldn't understand, but let me just code it, okay? Replace it by 0, okay? So this is what you're gonna do. Try it. Okay, now you see the first row is almost all 0 now. Let's check. The first row is, you see, all 0 except the third from the right. You see, let's go back to our matrix. You see, those one are gone, except that one. This one is also gone because it's got 3 neighbors. This one, you see, this one got 1, 2, 3, 4, so that one stayed. You see, so 0, 0, 0, and 0 and 1, 0, 0. So go back here. That is correct. So this is the code, correct code. Okay. So result matrix, this is wrong. This is correct. Now go back to previous occurrence. This correct code. Now remove the incorrect code. I think that's it. Then you just return result matrix and whatever. Okay. So now let's copy the whole thing and run it again. Select all, paste, just run it. 43, my friend. It says 43. Does it check? 43. Fantastic and beautiful. One shot coding. Well, it's like 3 shot coding. Okay, now we delete all these experimental like pad debugging part. Okay, we got it correct. Okay, actually we got our code, and this part, this we don't need either. This we got it correct. So this part, take it out, put it back, just for example's sake. We show how to use that delete. And now here, this is clean code. So that's that's the input. Turn it into a matrix. Define our get neighbors function. And for today's part 2 problem, description, algorithm description. And wait, why does it not? Yeah, my Xah keys is behaving incorrectly or something. Anyway, so algorithm description and the plan to how to implement this algorithm. Plan in Wolfram language, write the function ff. Ff will have this input form. That's in Java, they call it signature, which is idiotic. Okay. In mathematics, a function you don't call a signature. Well, you don't. Anyway, so function ff has this input form, one single argument of a list of two things. Okay, it will return a list, new matrix, and total remove cells count. Okay, then we just fixed point. This is recursion. This is supreme fixed point, even more supreme than Haskell. You know, Haskell and Racket Scheme Lisp, they are into recursions, but Wolfram language fixed point more supreme. Okay, so we define this function ff. This looks complicated, so you can go to Wolfram language and copy the formatted code. So click, 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 copy, and paste it here. So it's like formatted code better. Okay, remove that. And then you run that, and the result is what, 43? There it is. Okay, we need to copy the whole thing, and it shows the output. Fantastic and beautiful. So put it back, cut, paste again, syntax color the whole thing, and pop it out again. This time we're gonna do our personal input. And so what is my personal input? Okay, you need to go to search for txt there. So this copy, close, back to code. Okay, so you need to okay, string, paste, remove the last character. Okay, go to the top. Is that right? Yeah, go to the top. Yeah, input. So so this is copy the whole thing. Go to Wolfram language, select all, paste, shift enter, shift enter. Okay, inefficient code. Who cares? Because at the end of code, they don't care. Wait, how inefficient is this? You see, let's see. Every time you call this get neighbors, it recreates the entire matrix. That's how inefficient it is. But also, this get neighbors actually needs to get improved a lot, because this get neighbors, you know, it creates array pad. Every time you call it, it recreates the whole entire matrix. Okay, so to fix that, instead of creating array pad here, you should just array pad the input. Then this function just work on the padded array. So So every time this function is called, it doesn't regenerate a new padded array. It just use a global variable of the padded array. So that will significantly make it faster. Okay, this is not still not returning. No, that's problematic. It's like too slow. Okay. So anyway, so that's one problem. But there's also other inefficiencies because here you are deleting cases. You are deleting what is this? Delete cases. Oh yeah, so it's this part is actually just deletes the the cell itself except the neighbors. I mean, so it wants to return the neighbors, but it wants to delete the cell itself. So it has to look through all the neighbors, then delete the part. That's not good. So you should instead of using delete cases, you just should say delete nth. But if you code it that way, then this function will have difficulty in generalizing into n-dimensional matrix, because right now you see this function can be trivially generalized into n-dimensional matrix. So it's no longer just like get the neighbors of a two-dimensional matrix. We can have three-dimensional matrix or four-dimensional. This function get neighbors of a given cell can work on arbitrary dimension matrix. That's like the power of the Wolfram language. But this is inefficient. So the higher dimension is still no good. You basically you loop through all the neighbors. So if you have like 100 dimensional matrix, then for a given cell it has like 100 or whatever neighbors. That's another interesting question. Given a matrix of n dimension, how many then given a cell in the middle of the matrix, how many neighbor does it have? That's a mathematical question. Could be a advent of code question, but I don't think the guy is ever gonna have a question like that. You see, given a two-dimensional matrix, how many neighbor of a middle cell have? This is easy. I mean, if also we include diagonal neighbors, okay. But given three-dimensional matrix, how many neighbor it has, including diagonal, that can be easily found out. Let's say 1, 2, 3, 4, 5, 6, 7, 8. 8 at top, 8 at bottom. Then you're gonna have 1, 2, 3, 4, 5, 6, 7, 8. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 at top, 9 at bottom, 8 in the middle slice. So 9, 9, 8. 8 times 3, 86, 83, 24, that's 24. 24 plus 4, 2, you got 26. So you have 26 neighbors in three-dimensional cell. What about four-dimensional? Then you need to work out, okay? Then you can then you see a pattern. You can generalize to n dimension. How many neighbors? So let's write that out because it's an interesting problem. Question: how many n dimensional? How many neighbors a middle cell of an n-dimensional matrix has? Counting diagonals. Okay, this is interesting math question. Can be a coding problem. Well, it's not exactly a coding problem, but it can be. Then in that case, you have to like you try to code for a 3-dimensional matrix and 4th-dimensional, then you see a pattern, then you can write the function, But so it is interesting. Okay. Okay, so, but where are we? Did we get the final answer? We did. So it returned the answer. Yes, 43, because, wait, this, so this one got size in memory, 479 kilobytes. Oh, that's small. That's trivial. The Google, Google Chrome is like sucking 2 gigabytes. We are only talking about 1 megabyte. So the answer is 8690, okay? 8690. So show more. Wait, show more. Yeah, 8690. Okay, can you just get that? Oh, God. So we can actually, the last output, wait, where did we type it? Okay, so you just say the last output, and apply the function last, then we'll give you that number. 8690, please make it work. Are you sure? Yes, submit. That's the right answer. Yes, of course. Fantastic. Okay, nobody's here. That's well, that's sad. Okay, someone should congratulate me. Okay, someone, you guys. Okay, let's put the answer here. Okay, so we solved it. Put it back. Syntax color the entire code in the HTML page and show in browser. And let's summarize what we did today. And that's it. So we took about 2 hours. Actually, when did we start? So we did 1 hour and 30 minutes. Oh, okay. Not too bad. 90 minutes. Congrats. Thank you, the beast. That beast. Thank you. So summarize today's talk show, episode 732. Not too bad. Pretty smooth. The input, we showed the delete, whatever is input. So the input, we turn into a matrix of 1 and 0s. We use the get neighbors function we wrote before. Then we figure out the algorithm steps and the plan to implement the algorithm, which essentially relies on writing this function, one single function. And we use recursion of fixed point. Fixed point means apply the function to itself until the result no longer changes. Okay. Then it returns this, the result matrix and a number. The number is the total count of the cells that has been removed. Okay, then we use the personal input, and it takes a while. I don't know how long, but fuck advent of code, because if you pay attention, you work 5 hours to make it efficient. They don't care. Like, nobody would know your code actually is very different from all the other people who does it fast, because their code, they don't care about efficiency. So when you spend time on efficiency, you get punished. That is often the case with the Unix stuff, Unix and C, those type of people, because they don't care about extension. They don't care about design. They don't care about, they just care. They do care about fast though, but they don't care about the algorithmic efficiency, like the older, like, for example, a given problem, let's say you have your input is less than 100, okay, like the typical input. So the C and Unix type of people, and including C++, and pretty much the industrial coders, including Java, okay, but mostly C and C++, okay, what they care is that on average, all these inputs, their program is the fastest, okay, their program is just beats everything. We are fast. the C coders. Okay, but if the input becomes 1,000, like beyond expected input, their program may crash or takes a day to finish. But they don't care. Like nobody is ever gonna have the special like art input. Who is gonna do that? You know, they don't care. It's a C and C++ and the Unix fuckheads. They created a computing industry like that. Okay, so it's like bug, new version, patch, bug, new programming language based on C because we need to fix some problem in C and then C++ and oh, but Java. We need to create Java because C++ got this problem. Oh, but well, actually Java got all this problem. We need to create C#. That's all C, the daddy of all the problems, C and Unix. Okay, that is like my very biased point of view, but it is a point of view that has some merits. Okay, you can think about C and C and C++ and Unix, the origin of all the damage in computing, kind of. Okay, that's it. Bye, guys. If you like my stuff, okay, pay me. Go to my website, xahlee.info, xahlee.info. XAHLEE.info. Okay. HTTP no S, not secure because I'm not asking for your credit card. So you go to xahlee.info, then scroll down the bottom, then you go to Patreon website, Amazon gift card website, or PayPal. You go to their website, click. Their website is secure, so you can put credit card to it and pay me. Okay? Thank you for your support. Bye, guys.